All right. Good morning, and welcome back to Classical Mechanics 1 at CMI. Today is our 5th meeting. Today is the 16th of August, 2022. So I believe you have received your first problem set graded, and you are currently working on the second. Any questions before we continue? So, as I've mentioned before, attendance at our meetings is required, and I pay attention to who is present and not, and it contributes to your course assessment. Yeah. So let me just share my screen just a moment. I have to download a plugin. Okay. Any questions before we continue? Okay. If not, let me just remind you that last time we were towards the end, I think we were talking about circular motion, uniform as well as non-uniform, and also the idea of a rotation, how a vector under an infinitesimal change, if its length doesn't change, then it must undergo a rotation, and we derived some formulae for the rate of that rotation. Yeah, continuing this general excursion into preliminaries, I want to say a few things about what might one call kinematical equations. Yeah, so when one makes the distinction between kinematics and dynamics, and what are these two things, sometimes the distinction is a little bit blurred, but at least at this stage we can be somewhat precise about the difference. As we will soon learn, if the forces on a particle are known, then one may use Newton's second law to find its acceleration. Okay, so we have already defined the concept of a position of or location of a particle, its velocity, and then its acceleration. Now, if we know the forces in operation, then it's possible to find the acceleration. This is a consequence of Newton's second law, which we will introduce shortly. Now, this process of using the forces to find the acceleration is called the dynamical part of the problem of motion, since it depends on the forces and interactions. All right. So dynamics concerns the forces, the interactions with other physical bodies, the effects due to electric magnetic fields or gravitational fields present, all these things. They cause motion, and all of that is called dynamics. So dynamics can often refer to the time evolution of a system due to the forces in operation. Right? So dynamics is concerns itself with these things. On the other hand, the kinematical part of a problem of motion is to determine the velocity of the particle and its trajectory from the knowledge of its acceleration. Okay, so this is one part of the kinematical aspect of a problem. So here the forces are not relevant, or at least their role has already been played in finding the acceleration, and our job is to go from the acceleration to velocity and say the trajectory itself. So that is that part is called kinematical. Yeah, but I mean, there's more to kinematics. Kinematics, we will say more as we go. We are going to introduce other terms as well. Yeah, so I will say more on this this distinction, these concepts. But for now, we will address this question. So suppose we are given the acceleration of a particle. Then the velocity must satisfy dv by dt is equal to a of t. Okay, so the acceleration itself can is of course a vector, and it can depend on time. This is a basic observation, and so our job is to solve this equation, and this is a differential equation. Can you tell me? Do you want to tell me anything about this differential equation? Can you give me any of its attributes or describe it?
Rate of change of velocity per unit time.
Sure. Now, that is true. That is the acceleration. But I want to know, okay, who answered that? Sorry.
It's separable.
It is separable.
Greenish.
Okay. Yes, it is separable in the sense that you are tempted to take dt to the other side. Yeah, and dv is equal to a of t dt. That's your idea of separability. Is that right?
Yes.
Yes. So that is true in that sense. Sorry, who spoke, please?
I'm Anhad.
Anhad Chaturvedi, is it?
Yes.
Okay, great. And you are at CMI, if I understand right.
Yes, I'm at CMI.
Okay. Yeah, I think I missed you in one of the earlier lectures, but I'm glad you are here.
Did I? Wait.
Okay, maybe you were present. Fine. Okay. So you have rightly pointed out that this has a feature of separability in the sense that yeah, the time can be taken to one side, and so what is t in this problem? Mathematically speaking, we give a name to the t variable in such an equation.
Independent
variable.
Yeah,
independent variable.
Independent variable. Yeah. Yes. And okay, since there's an independent variable, there must be also a different type of variable, which we shall call what?
Dependent variable.
Yeah. So which one is the dependent variable here?
Velocity.
Velocity.
Very good. So velocity. So v here is a vector, is the dependent variable. Yeah, because it depends on time. Yeah. On t. Okay, so that's why it's called the dependent variable. Sometimes we say, what is the unknown quantity in this equation?
The velocity at time. Velocity, sir.
Yeah, indeed. So the three components of velocity are the unknowns. Yeah, so those are the unknown quantities. They are the ones we wish to determine. And this is a differential equation. Can you qualify what type of differential equation it is?
Single order differential equation.
Single order, yes.
Yeah, I would call it, you said single order. Yeah, okay, have some other suggestion? Single order is basically correct, though the term that we tend to use is not single order.
Linear difference.
Okay, this is also a very good idea. Just a moment, before we go to that, I want to comment on this word.
First order.
Yeah, we usually call it first order. First order. Yeah, first order differential equation, in the sense that it involves only the first derivative of the unknown quantity. Yeah, first derivative of v, which is the unknown quantity. So that's why it's called first order. And somebody said it is a linear. That is also yeah, that's also a nice point to be made. It's linear in which quantity?
In time.
In time, sir.
Is it linear in time?
In terms of velocity, right?
No. No, sir. In acceleration.
Sir, in
Acceleration.
velocity,
Yeah. So,
dv by dt.
right. So wait. It is linear in d by dt, but that is the statement that it is first order. First order means involves only d by dt, not d by dt squared. D by dt squared would be a second order operation. So first order means only involving first derivatives. But on the other hand, we also said it is a linear equation, or some of you suggested it's linear. It is not linear in time. That is not what we are referring to. In fact, a of t may be a complicated function. Yeah, like a of t may be t squared, yeah, some up to some constant, t squared times alpha. So since we have not specified a of t, we cannot say it is linear in time. So we have to let go of that possibility. When we say it is linear, we are saying it is linear in the dependent variable. So this equation, that is v dot is equal to a, is linear in v. Okay, so because v appears only the first power in the equation. A is a prescribed function. A has been given to you, and our job is to find v. For that purpose, the equation is linear because it appears, v appears only to the first power. Is that, yeah, are you clear about what I mean by linear?
Yes, sir.
Okay, great. Yeah, so we can add one more attribute. I will say also it's not just first order and linear, it's an ordinary differential equation. Ordinary differential equation. Ordinary because there is only one independent variable, namely time. Only one independent variable, namely time. Okay, if there's more than one independent variable, then it does not qualify as an ordinary differential equation. It is called by a different name, which you can suggest to me.
Partial differential equation.
Indeed. So that who was that?
Dvitimaya.
Dvitimaya Sahu. Yes. Yeah. So indeed, if there is more than one independent variable, then it becomes a partial differential equation. But right now we are dealing with this one. So this is ordinary. Okay. So we have made our acquaintance with this differential equation, perhaps one of the first that we are studying. And now we can integrate this equation. After all, it's a differential equation. We wish to solve it. That would involve some sort of integrating this equation with respect to time and using the separability, basically taking dt to the other side, multiplying the acceleration by dt, and then integrate. We will get on the left-hand side integral dv from some is equal to integral a dt. We go from some t naught to t. For good measure, we will denote the variable of integration t prime to not confuse it with the upper limit of integration. Yeah. So then when you integrate it, the left-hand side will give you v of t minus v of t naught. So that's what I've written here. I've taken the v of t naught to the right-hand side. So v of t is simply v of t naught plus integral t naught to t a of t prime dt prime. Okay, so we have exploited the separability to do this. Any question about how we did that? Again, I mentioned that a of t, the acceleration, is a prescribed function of time. We are not concerned with how it is to be determined. That is a dynamical part of the problem. We noticed that in addition to the knowledge of the acceleration, we also needed an initial condition, namely the velocity at the initial time, to solve this equation. We need to know the velocity at the initial time in addition to the unknown acceleration. I mean, in addition to the acceleration. In fact, we actually need three initial conditions, namely the three Cartesian components of the velocity at the initial time. T naught is called the initial time. So such a problem is called an initial value problem. Yeah, initial value problem in the sense that the initial value of the unknown is given to you, and you find the subsequent behavior of that quantity. Yeah. Now, the problem of determining velocity has been reduced to simply performing integration. So this performing integration goes by a fancy name. It is called quadrature. Quadrature is the fancy name for integration. Yeah, so we have to evaluate integrals. In fact, we have to evaluate 3 integrals, one for each of the 3 Cartesian components of the acceleration that appears over here. So now we are not saying that that integral is easy to evaluate or can be evaluated in closed form and so on. That's a separate question. But formally, we can write down the velocity at any time in this manner. The job of computing that integral then becomes an interesting separate problem for which there are many tools. Okay, any questions so far?
Why do we call them quadratures?
Why do we call it quadrature? Okay, no, see, that is simply another name for integration. So if you are asking for the origin of the word quadrature, I am afraid I have to recall and go and look it up. I don't remember, but that is the traditional word for integration. And it, yeah, I mean, Gauss used it. I mean, Gaussian quadrature. These are that term is commonly used in mathematics, applied mathematics elsewhere. I mean, is that what you were asking? What the?
It's not like quadratic. It's not related to that.
No, it is. No, I don't. Okay, I should not hazard an informed guess over here. On the face of it, it is not related to quadratic. Though there could be some more involved way in which things are related to quadratic things, but we are not assuming that the function is quadratic or anything like that. Quadrature is simply the act of performing an integral. That is a name for this process. Yeah, but it is interesting to know the history of this word. Okay. Yeah, Vedant Nima has enlightened us that quadrature is a historical term, which means the process of determining area. Okay, great. Yeah, so quadrature is determining area, and determining areas was one of the historical motivations for the theory of integration. Yeah, so thank you for that. I don't know whether that still sheds any light on the origin of the word quadrature itself. I'm sure there is some good reason. I hope so, at least. Okay. Any other comment?
Sir, actually, it says that it is related. They used to find areas by comparing it with the area of a square. So,
okay, quadrilateral. Perhaps.
Greeks used to do that. So,
okay. Nice to know that. Fine. Yeah. So perhaps to find areas, they used to approximate the region by squares, which of course have 4 sides. So they're the quad. Yeah, quadrilaterals. So yeah, that sounds like a nice word origin. Okay. So thanks for enlightening us. What was that, Vedant?
sir, this was Vishnu Ravi, sir.
Vishnu Ravi. Okay, fine. Yeah. So Vishnu Ravi. Vishnu Ravi is not here. Okay. I mean, not in Chennai, at least. No, at least not at CMI. By the way, the students who are at CMI, I would like to meet you. Could you please just briefly come to my office? I don't mean all together, but at random times, and just at least so that I know who you are. Okay, coming back to our process of integration of kinematical equations. The step from velocity to position, see, we have taken one step, namely from acceleration to velocity. And now we want to take another step, namely from velocity to position. This involves one more integration and another initial condition. So the equation to be solved is r dot equal to v, and the solution in the very same manner is r of t is equal to r of 0 plus integral t naught to t v of t prime dt prime. So and in this process, we have introduced yet another initial condition, which is the initial position of the particle. So initial position of particle. Yeah, so evaluating these integrals for a specific acceleration function, namely a of t, may or may not be feasible analytically. And that is where quadrature comes in. You can't evaluate it using some simple rules that you learn in school. There may be more fancy methods needed, or you may need to break up that area into little quadrilaterals and add them up and so on. So that's where quadrature comes in. Okay, so now in summary, we have solved the second order ordinary differential equations, namely r double dot second derivative of position equal to acceleration. Yeah, so it started out as a second order differential equation, 2 time derivatives. We have solved that in 2 steps. Yeah, first step we go to velocity and then to position. So being second order, the process required 2 initial conditions or 2 pieces of initial data, namely the initial velocity and the initial position. Though I say there are 2 pieces, each of them itself is a vector. Okay, so each of them is a vector with 3 components. So in effect, you need 6 pieces of initial data. When I say pieces, I mean really 6 real numbers. Real numbers. You need all of that in order to perform this integration. Okay. Now I will mention a simple example, which I'm sure you have seen before. A simple example is that of uniform acceleration. When we say uniform, we basically mean an acceleration that is independent of time. In other words, a constant vector a of t is a constant vector a. In this case, v of t, that integral a of t prime dt prime can be performed very easily. You just get t minus t naught times the acceleration vector. So that gives you an explicit formula for the velocity at time t. And now integrating once more the equation r dot equal to v, we will get r. So you just have to integrate both these terms. I will just write down the answer and leave you to do this. There's of course the initial condition r of t naught plus when you integrate this term, v of t naught is just a constant. So you will get t minus t naught times v of t naught. And then you have to integrate this term. There are sort of yeah, I mean, you have to write the integral and evaluate between the limits. And I claim that you will get 2 terms. One is 1/2 t squared minus t naught squared a, and then minus t minus t naught times t naught a. So I leave you to check that. So we have got, we have solved the kinematical problem of going from acceleration, a uniform acceleration to the location of the particle. And this is the full formula. The formula simplifies if the initial time happened to be 0. So and this is a very useful simplification. Many, I mean, it's a very remarkable fact about nature that the results of physical experiments, which are which do not depend on certain details, are reproducible. Okay, so they are reproducible in the sense that whether you do it today or tomorrow, yeah, or had done it 2 years ago, you get the same result. Okay, so there is a kind of independence with respect to time. Yeah, certain physical phenomena, and you can choose the zero of time as you wish, and choosing it to be zero, t naught to be zero, just simplifies this formula. Yeah, that's I mean, I'm saying different things here. I said a much deeper statement about time translation invariance, but choosing t naught as zero is a much more mundane thing. It simplifies this expression and brings you to a more familiar expression, perhaps. R of t is the initial location R naught plus t times v of 0 plus half a t squared. Okay, so that's a very familiar formula from your initial education, I would think. But it's very important to bear in mind that this formula applies to the case of a constant acceleration. If the acceleration were not constant, there is no such, I mean, the formula would be more complicated or even not expressible in such a simple way. Okay, so this is what I wanted to say about the integration of kinematical equations at this stage. Any questions? Okay, if not, I wish to now say a bit about polar coordinates, both on the plane and in 3 dimensions. These are very useful, and they take a little getting used to. So let us begin that process. Yeah, so let's first talk about plane polar coordinates. Now, for many purposes, for many problems, especially those where there is rotational symmetry around a central object. Yeah, so can you suggest some physical problems which have such features? Some kind of central object playing an important role.
A merry-go-round.
Planets. Planets.
Yeah, you've given 2 interesting ones. So one is a merry-go-round. Yes, indeed. So there is an axis, or and then the seats are attached to that axis. So there is indeed a central object there. As I also pointed out, the motion of planets around the sun also has a distinguished central object. Indeed. Any other suggestions?
Sir, a fly around a candle fire.
Okay. Sure. All right.
Sir, of
Yes.
electrons,
Yeah.
I think. Sir, of electrons around the nucleus.
Yes. Very picturesque examples you have suggested. A fly attracted to a fire. Okay. And now somebody has mentioned electrons in an atom, right? Am I right? So yeah. So these are all very interesting examples. Okay. So
wave,
sorry?
microwave, microwaves,
Microwaves. I think you would have to say a bit more so that I can understand.
point source.
Okay. A
And
point source of microwaves. Fine. Okay. Yeah. So yes, a point source of whatever, maybe water, maybe electromagnetic waves. Yeah. There again, it might be quite helpful to use polar coordinates. You're right. Okay. So where there is some kind of point source or a point sink, those are definitely candidates for such treatments. Okay. Now, for simplicity, let us consider polar coordinates on the plane. Now, these are called r and theta. Now, suppose we are given an origin O, so that's very important. That origin is usually then located at the central object, which is regarded as a point, or maybe at each center. This may be the sun or the nucleus or the point source of other things. So given an origin O and a horizontal and vertical coordinate axis, Cartesian coordinate axis X and Y. So let me draw a picture. We have an origin O, we have the X and Y axes. Yeah, and then we have a point P with Cartesian coordinates X and Y. Then R is the radial distance from the origin to P. Okay, so that distance is R. And that takes care of R. Of course, R is equal to the square root of x squared plus y squared. You will agree. Furthermore, the angle theta is the counterclockwise angle that the radius vector r equal to x comma y makes with the horizontal x-axis. So this is our agreement to measure the angle theta counterclockwise from the horizontal axis. Okay, so you could of course do it differently, but this is a fairly standard convention to go counterclockwise and to measure it from the x-axis. Now the position of the point named P is associated with the position vector, which is denoted R. What happened? R. Yeah. Okay. Now let me proceed. Yeah. Let me. We are going to recall. I already introduced this term that x coordinate is also called the abscissa, and the y coordinate is also called the ordinate of the point P. Now these terms you will meet here and there. So I'm just familiarizing you with those terms. So by looking at this little triangle with the horizontal length x and vertical y, this right triangle, you conclude that y is equal to or the tangent of theta is equal to y upon x, and the cosine of theta is x upon r. Yeah, so these are elementary consequences from trigonometry. So we could say that the theta, the angle theta, is the arc cosine of x upon r, or also the arctangent of y upon x. Okay, so this is just the setup of the coordinates. Of course, x is r cosine theta and y is r sine theta. So all this I hope is understandable. Any question about the setup? Okay, let us just notice here a technical point that theta is defined modulo 2 pi. I could go all the way around and back here. Yeah. So it's defined only up to an addition of multiples of 2 pi. In other words, theta equal to 0 and theta equal to 2 pi both correspond to the positive x-axis. So there is a redundancy here. So one often chooses a convenient fundamental domain for theta, such as the closed open interval from 0 to 2 pi. So, or you could go from minus pi to pi. Yeah. So you have to use some convention if you want to fix a particular angle. Yeah, and depending on the problem, there may be various convenient conventions. Okay, now it is important to observe that the polar coordinate system, we say, breaks down or is singular at the origin, where x and y are both 0, as is r. Okay, so r is also 0 over there. At this point, the angle theta is not well defined. It's not even defined. In a sense, the point at the origin could be assigned any value of theta depending on how we approach the origin. So this is the origin, and I approach the origin along different curves of constant theta. Let us say I approach along a curve of constant theta. Then theta didn't change at all, so I may assign that value of theta to the origin. But there are many ways of approaching the origin. So the origin does not have a single value of theta. So said differently, the map between xy on the one hand and r theta on the other hand fails to be 1-to-1 at the origin. So there are many thetas that correspond to the same x equal to 0, y equal to 0 point. So there is this technical issue which one has to deal with when one gets to it. Okay, so that was just a technical aside. We will come back to it when necessary. Now let us do other more important things. Notice that the constant x and constant y curves in Cartesian coordinates, okay, the constant x and constant y. So if I if I look at a constant x curve, a curve along which x is constant, well, that would be a vertical line. Yeah, so x equal to 1, x equal to -1. Yeah. So we notice that the constant x curves and the constant y curves, constant y's are horizontal curves. I mean, they're lines, of course, just call them curves here. They are mutually orthogonal straight lines parallel to the y and x axes respectively. The curves of constant x and constant y are mutually orthogonal curves. These curves are also called the level curves of x and y. A level curve of x is a curve along which x is level, that is, x doesn't change. Any question about this terminology? Okay, now let us extend this to the polar coordinates. We can ask, what are the constant theta curves? Theta equal to constant curves are rays emanating radially outwards from the origin. Yeah, we can take them to be outward. I mean, that's just a convenience. Yeah, so this curve emanating radially outwards. Let me clean up this figure.
Do these rays contain the origin?
See, on the origin, no, strictly speaking, no, because at the origin, theta is not well defined. So at the origin, theta, yeah, we might omit it. Yeah. So there are rays that exclude the origin, you might say. So on this ray, theta was some pi upon 4, you might say. And along this ray, theta was pi upon 2, and so on. Theta equal to 3 pi upon 2. And here theta is 0. So you got lots of these rays. So these are the theta level curves. Theta level curves. On the other hand, the constant r curves, if r is a constant, then you get x squared plus y squared equal to constant. So these are circles when r is a constant. In fact, they are concentric circles, all centered at the same origin. So the constant r curves are concentric circles centered at O. Yeah. So for this reason, polar coordinates are called curvy linear coordinates because the level curves of theta of r are not straight lines, they are curves. I mean, here they're circles. Nevertheless, despite being curvy linear, the level curves of r and theta are still mutually orthogonal. That feature is still valid. I'm just pointing it out, just like it was the case with x and y. Okay. Yeah, now I want to bring in one more concept. Now a real valued function on the plane is simply any function of x and y that assigns a real number to each point. Point xy, you assign some real numbers, could be x squared plus y squared, could be xy, yeah, could be the sine of x, etc. Now this yes,
f of x comma y, you mean multi-variable function?
Yes. When I say a real valued function, I mean a function of x comma y. It is a function of two variables, but its value is just one real number. So an example of this may be simply x squared y squared. Okay, so this is a legitimate function of two variables. Does that address your question? Okay. Yeah. So the simplest of these functions are the so-called coordinate functions, x and y themselves. So if f of xy is simply x itself, then yeah. So there's a question I will address in a moment, just a moment. So the function f of xy, which is x itself, is called the first coordinate function. And the second one is f of x comma y equal to y. Okay, so these are two of the simplest functions. They are called the coordinate functions because they assign the value of the coordinates themselves. So in Cartesian coordinates, you have two coordinate functions. And similarly, any function of r and theta, it can also be considered. Of course, that function should be such that it is defined modulo 2 pi in theta. Okay, so it must assign the same value whether you say theta equal to 0 or theta equal to 2 pi. Yeah. So, but if f of r comma theta is r, then that is also a coordinate function. Okay. Now that is simply a terminology. If you're not comfortable with it, don't worry about it right now. Okay, I have a question from Shyam Patankar. How are the level curves of r and theta mutually orthogonal? Okay, please examine this figure carefully. I think you will agree with me that this is a level curve of theta, namely where theta is pi by 4. This is a level curve of r, a circle of radius, let us say radius 2. Now you will notice that this angle is 90 degrees. So also between this circle and that ray. And this is true wherever you go. Okay, so it is in this sense that the level curves of r and theta are mutually orthogonal. Is Shyam satisfied?
Yes.
Okay, excellent. Okay, so so despite being curved and all, the coordinate level curves are orthogonal to each other. Okay, let us now go to the next stage. We want to talk about unit vectors. Remember, we already introduced unit vectors x hat and y hat. So these were the unit vectors along the two Cartesian coordinate axes. And we want the analogous concept for the plane polar coordinates. Okay. So recall that at a point x comma y on the plane, x hat and y hat are unit vectors in the directions of increasing x holding y fixed, and increasing y holding x fixed. Okay, so that is how we would like to think about these two unit vectors. Similarly, we would like to define the unit vectors r hat and theta hat at any point r comma theta. So given a point in the plane, it has some r and theta coordinates. R may be 1 and or let's say 2, and theta may be some pi upon 4. Okay, so that gives you this location. At that point, we want to define r hat and theta hat. Okay. Now in words, r hat should point in the direction of increasing r holding theta fixed. Okay, so that is the basic idea. And similarly, theta hat should point in the direction of increasing theta holding r fixed. Okay, is the definition or the idea clear?
So how will you write this point which you have drawn here in terms of r hat and theta hat?
See, a point. Oh, very good question. The point P, which is, let us first write it in XY coordinate system. Yeah, how will you write it in XY coordinate system? Please tell me.
2 cos pi by 4 x hat and 2 sin pi by 4 y hat.
Okay, wait, you have gone very far. I want to do something more elementary. Okay, forget about this specific example. I simply have some point here, x comma y. And that is my point P, x comma y. So I think you will agree with me that if I denote the position vector of that point by the vector r, then r is equal to, I want to write it in terms of x hat and y hat as a linear combination of x hat and y hat. See, x hat was this vector and y hat was this vector. So please tell me what linear combination I should take to get to this point.
Yeah, here it is simple x and y there.
Yeah, x hat plus y hat, right? You are you're happy with that? Okay, very good. Now I want to write the same vector. Yeah, the vector representing the same physical location in our polar coordinate system. So tell me, what it has to be a linear combination of r hat and theta hat. Now I have not yet told you what r hat theta hat, but you seem to have sufficient intuition. So please tell me what the coefficient should be. Do you want to make any suggestion? Okay. Yes, please.
R hat and theta hat. So
Yeah. See, let's do the XY story once again, right? What is this telling you? It's telling you go a distance X in the X hat direction, then go a distance Y in the Y hat direction. Okay, that's what it's telling you. It is telling you to follow that recipe. Similarly, we need this. So, okay, maybe I have to take a moment and tell you what R hat and theta hat are. So first tell me, suppose I have a point here. Which way does the R hat vector point?
The length.
along the length, yeah.
Yes. Let me say radially outward. Okay, I think let us call it radially outward.
R is
Yes.
the root of x square plus y square. So that's
Yes.
what r hat will be multiplied by, and theta is r tan of y over x.
Mhm.
So that's what theta hat will be multiplied by.
Okay. Well. Okay, I'm coming to that. I think we need
So
to.
is R hat just a unit length along the?
Yes. R hat is a unit vector. R hat is a unit vector, so it has length 1. Okay, so if this is
then there will be R, the length of the R hat.
very good. And then what is the coefficient of theta hat?
Theta hat will be so. Similarly, definition should be 1 radian. Is that it? Counterclockwise 1 radian.
No. Let us think. Let me. Okay, I have told you which way R hat points. Please tell me which way theta hat points at this point.
So, but by general notation, it is perpendicular to the plane.
Perpendicular to the plane.
Perpendicular to the R vector.
Perpendicular to the R vector.
R
Yes,
vector.
that is
Yes.
true. That is true. But no, let's go back to the definition. R hat points in the direction of increasing R holding theta fixed. Okay, that is the story. So I do that story here. Go here, go in the direction of increasing R holding theta fixed and draw one small vector there. If I do the same thing for theta hat, I must go in the direction of increasing theta holding R fixed. So tell me, which way does this theta hat vector point? You can tell me.
Counterclockwise.
Very good, counterclockwise. Indeed. So from here it will point this way. Okay, so that is the theta hat direction. Okay, so now please give me a suggestion. What am I to put here?
Tan inverse y by x.
Sahil has given a suggestion, but please try again. Look, the vector we are wishing.
Sir, R theta.
Oh, here you are suggesting what to write. Something like R theta, is it? You said we have had many
Yes.
suggestions. Tan inverse y upon x. You have got R times theta. No, I want.
Sir is 0, right?
0 is a better suggestion. Okay. So yeah. So okay, let me tell you why 0 is a good suggestion. See, the job is already done. Yeah. After all, remember the R hat vector by definition is the R vector divided by its length. Nothing more to do. Simply take this that side. Okay. Is that all right?
Yes.
Yes, sir.
Yeah. See, I mean, after all, the R vector points radially outwards. It doesn't have any angular component at all. Yeah, so there is no azimuthal component.
But
There is
it's only r vectors, right?
Sorry, Anhat, please repeat.
You could have an r vector for any angle. Like
Yeah, exactly. Yeah, this could be anywhere. This R vector also has the same property. That R vector is R times R hat. So this is a general formula.
So wait, aren't we taking a coordinate plane and representing, say, the x-axis as r or the y-axis theta or something like that? Since you're writing the notation as r comma theta, is that not what we are doing?
Yeah. So see, this is a point, right? So there's a point P. It has coordinates r comma theta. So at that point,
point C had coordinates x comma y.
as well as r comma theta. Yes, they are two interchangeable sets of coordinates, right? So at this point,
So is this point in the coordinate plane of r comma theta or in the coordinate plane x comma y?
see, the coordinate plane is a God-given physical object. You may like to call it xy plane, r theta plane. That's all your bias. Yeah, the plane is the plane. Now, on this plane, you have an origin according to our convenience. We have a point P. We want to give its coordinates or the position vector of that point P in the manner of
Wait.
our choosing.
But points in the coordinate plane of r comma theta won't be vectors, right?
No, see, you're right. A point is not a vector. However, the line from the origin to that point with the directed towards that point is a vector. We want to describe that vector. That vector is called the position vector. That position vector has two descriptions depending on which coordinate system you use. That position vector on the one hand can be called x hat plus y hat for reasons I explained, but it can also be written as simply r hat. Is that okay, Anhad, or whoever was asking? See, both of these are ways of talking about the position vector r. Now, you may ask, what is the value of r for a specific point? Yes, in that case, we have to be more specific. This r may be 2 meters. Yeah, and in that case, this x and y will have some specific values, right? X and y may be. Two numbers, the sum of whose squares is 2. Okay, so
can we say r represents the magnitude of r vector and r hat represents the inclination?
okay, yeah, I think some of the notation is getting a bit unwieldy. So when I say r, I mean the magnitude of the r vector. When I say r hat, I mean the unit vector along the r vector. So is that clearer, Sahil?
Yeah.
I wouldn't say the r hat has information on the this direction. Yeah, r hat, which you called inclination. You called it inclination. Somebody may call it direction. Yeah. Okay. Good. And yeah. Okay. So this takes some getting used to, but we are doing precisely that. So please continue to pose questions because we are soon going to do some more fancy things. Okay. Now let me continue with these comments unless you have some other question. See,
so one thing which I wanted to ask is that x hat is unchanging with respect to time, but r hat might change.
okay. Yeah, see, right now there is no time. We are simply taking points and assigning some unit vectors to the position vectors of those points. Yeah, but you are on the right track, very much on the right track. One can now think about a particle moving in this place, tracing out some curve, some trajectory, and that at each point of that trajectory, you may have its x hat and y hat vectors, and also r hat and theta hat vectors. And you are quite right, and I'm going to expand on that. There is a sense in which r hat and theta hat depend on location. And if that location depends on a trajectory or time, then they will depend on time, whereas x hat and y hat do not. So yeah, that was Ryan, was it?
Yes, sir.
Yeah, yes. So Ryan Hota, you will see. I will expand on the answer to your question in a moment. So let me just comment here that x hat and y hat furnish one basis for vectors at any point on the plane. Okay, so you take any point on the plane, such as this one, you've got the x hat, y hat basis. Okay. Similarly, r hat and theta hat furnish another basis at any point, excluding the origin. See, because origin is a bit bad, over that point, theta becomes ill-defined. So if you leave out the origin, then r hat and theta hat also furnish a basis of unit vectors, orthogonal unit vectors. And therefore, we can expand r hat and theta hat in the x hat, y hat basis. So by definition, a basis was a pair of vectors here, pair of orthonormal basis unit vectors. such that any vector can be expanded as a linear combination uniquely. So here, let us do that. I am going to write r hat as a linear combination of x hat and y hat. Okay. So I hope you will agree with this formula, and it is motivated by the picture. So let's come to this picture. I have a point here. X hat points this way, y hat points that way, and r hat points radially outward. They're all unit vectors. So now we can look here in the picture and immediately resolve r hat into its x hat and y hat components. Yeah, you will notice that this distance is cosine theta and this distance is sine theta. Okay,
Yeah,
so
actually, what you have written is that just rotating the x hat y hat frame by theta angle. You'll get
yes, you are right. Right. Let me say what Onkon said a little bit more precisely. If you take the x hat vector at this point, the x hat vector at this point, and rotate it by an angle theta, I will get the r hat vector. Okay, so I think that is a fair statement, if that is what you meant.
But that in turn gives the sense of direction, no?
Yeah, because theta has been regarded as counterclockwise. So yes, rotating theta counterclockwise will take you from x hat to r hat. Yeah, the sense of direction is given by that. Yes. Is that what you were asking, Sahil?
Yes, sir.
Okay. Okay. So we have got a very important first formula, namely that the r hat vector, unit vector, can be expressed as cosine theta x hat plus sine theta y hat. I mean, yeah, I have said in what sense this is a rotation, but I don't want to regard it as a rotation here. It is simply a component-wise orthogonal decomposition of one vector in terms of a basis. Okay? That is the way to think about it over here. It has some interpretation of the rotations, which we have mentioned, but I don't want to focus on that right now. Of course, we can rewrite cosine theta as x upon r and sine theta as y upon r. So that is an alternative expression. Okay. Are you all with me?
Yes, sir. Yes, sir.
Okay. Thank you so much. Yeah. I hope you speak for others as well. I do encourage all of you to participate in our meetings and offer your comments or questions or answers. Yeah. Now let us move to the second unit vector, namely theta hat, and resolve that into its x hat and y hat components. So again, we are going to use the picture. According to this picture, theta hat points counterclockwise from that point. Yeah. And we have to then find its x and y components. From the picture, please advise me, is the x component positive or negative?
Negative, sir.
Negative.
Very good, very good. So the x component is negative and it has this magnitude. That magnitude is given by what quantity?
Sir, minus sine theta.
Very good. So minus sine theta, which is precisely what has been written here. Thank you so much. Was that Krishanu?
Yes, sir. Krishanu.
Krishanu Bandyopadhyay. Yes. Okay. And similarly, the y component of this theta hat vector is the cosine of the angle, cosine theta. Okay. Okay.
Sir, it can be thought like that the r cap vector, that one, the theta is increased by 90, the angle is increased by 90 degree clockwise. So theta will be equal to cos theta plus 90 x cap plus sine theta plus 90 y cap.
Yes, you're right. Yeah. So to go from theta hat to r hat, you have to.
R hat, yes.
No, to go from r hat to theta hat, you must counterclockwise,
focus
90 degrees.
Yes.
So you are doing precisely that. You are going from this equation to that equation,
yes,
by augmenting theta by 90 degrees. Sure, you can think of it that way. So you don't have to look at the picture twice in a sense. No, I would say you should keep on looking at the picture, and all results will be clear to you. Okay. All right. And you are also welcome to express sine and cosine in terms of the Cartesian variables x and y. So that's what's been done here. Okay. So we have made a lot of progress. We have obtained a transformation formula between the unit vectors in the Cartesian frame and the unit vectors in the polar coordinate system. Now I will comment on a geometric observation that we already made, right? We said that the level curves of r and theta are mutually orthogonal. That translates to the statement that the unit vector r hat and the unit vector theta hat must be orthogonal. Okay, so they are essentially the same statement. Let us check whether our formula respects that geometric observation. We have got some r hat vector, we have got some theta hat vector. Are they orthogonal? Well, to check, simply compute the dot product. Let's do that. If I take the dot product of r hat with theta hat, yeah, we are going to get x hat dot x hat term, which will be cosine times minus sine. So let's compute this. We're going to get cosine times minus sine minus cs x hat dot x hat. Okay, then we are going to get plus sine times cosine plus sine times cosine y hat dot y hat, and finally two cross terms. But what can you tell me of the cross terms? Namely x hat dot y hat.
It is
They
0.
will be 0.
They're 0 because x hat and y hat anyway are mutually orthogonal. Okay, so I will retain only these two terms. X dot x is 1 and y dot y is 1. So you get minus cs plus sc, that whole thing is 0. Okay, so we have verified that r hat and theta hat are indeed orthogonal to each other as the picture already demonstrated. Not only are they orthogonal, they are orthonormal because they have a unit length. That again you can check from the formula. The length of this vector r hat is basically the sum of the squares of its x and y components. So that is equal to 1. So here we are. We have found a new orthonormal basis for the plane at any point on the plane. Okay, now I want you to tell me a right-handed orthonormal system. Yeah, please tell me, as you remember, when I say right-handed, you are always thinking of an ordered basis. So please tell me a right-handed orthonormal basis. Okay, maybe I'm being a bit silly here. There's only 2 dimensions. But anyway, if z is out of the plane, yeah, x, y, z, so what must the order be so that the system dash dash z and dash dash z is right-handed? I want it in Cartesian and polar. My question is not clear. Ooh.
So could you repeat? I did not understand.
Yeah, my question was very poorly stated. See, we have got a frame, right? X hat, y hat, and now I include also z hat. Okay, now, in what order must I put them so that they form a right-handed system?
R, theta, and z.
Sir,
Indeed.
r, theta, and z.
Yeah, so you're right. So if I take r as my first vector, theta as my second vector, I hatted, of course. Then if I take the cross product, r cross theta.
R cross theta is equal to z.
Z, indeed. So the order must be r hat, theta hat, z hat. And if I work in Cartesian system, what is the order?
X hat, y hat, z hat.
Indeed, x hat, y hat, z hat. Yeah, that we already saw. So all I'm saying is that the order does matter. And if I want a right-handed system, I must put r hat as the first and then theta hat as second. That's all I was saying. Okay, so any questions so far?
Sir, one.
We have 2 people question. Yeah, so one at a time, please. Oncon, you have a question?
Yes, sir.
Please go ahead.
No, sir. Here you wrote in the Cartesian, you wrote x hat, y hat, z hat, and
Yeah.
in the other polar coordinates, won't z hat be replaced by another angle? I mean alpha hat or something like that.
No, but you can call it what you like. But what is r cross theta? R hat cross theta hat? Yeah, geometrically speaking, which way does it point? We are asking.
Yeah, that's fine. That's
That is fine. That is simply Z. So be happy with that. We have R theta Z. Now you may ask, you somehow like to have one more angle. That is fine. That is your feeling on Tuesday morning. But this is a perfectly fine coordinate system. It has a good name also. Does anybody want to propose a name for it?
A cylindrical coordinate system.
Yeah, cylindrical polar coordinates. So R theta Z is called cylindrical polar coordinates. So the axis of the cylinder is along Z, and then you have R and theta on the horizontal plane. Yeah, well, I think what Ancon is going towards is spherical polar coordinates. Yeah, so those are a different system which we will address after a little bit of time. Okay, are you okay, Ancon?
Yeah. Okay.
Sir,
Okay, Ryan has a question, please.
yeah, so I was asking a basis, so I can, in basis contains in this case two vectors,
Yeah.
and I can and the basis is supposed to represent any location on the plane with a linear combination of those two vectors.
Yeah.
Right.
Yeah.
So could you please show me, sir, how would you represent maybe 1, 2 and 2, 1 using this basis?
Okay, so you want to look at an example. So the point 1, 2 is, so this is 1, this is 2, this is 1, this is 2, 1, 2, 1, 2 is this point, and 2, 1 is this point. Are those the point you have in mind?
Yes, sir.
Okay, very good. So then first of all, we draw the position vectors of these 2 points. Got a bit messy. Let me clean it up. Yeah, I think let me do one of them, then you can do the other. Yeah, let me do one at a time. Okay, so this this point P, the radius vector or position vector, I can write it in 2 ways. One, I can write it as, well, do you want to tell me what it is in Cartesian variables?
It's 1, 2. Right?
Yeah, that is 1, 2, but I want to write it as x hat plus 2 y hat.
Yes.
Are you okay with that?
Yes, sir. Sure, sir.
Okay, great. So this is x hat plus 2 y hat. So that's a very explicit formula for this position vector. Now, but you also want to write this formula in in plane polar variables. So I must put some r hat here and theta hat here and ask what are its coefficients. Do you want to suggest any answer?
Yeah, my question was not specifically about the answer. My question was, like, when you are representing 2 points which are not on the same ray from the origin, we are using different bases, right? We are not using the same basis.
Okay.
Right. So how can we call it a basis if it can represent any other, like, multiple points in the plane?
Yeah. So I am being a bit wishy-washy with these things. Yeah. So yeah, see, one can try to be much more careful and precise. Let me add a few remarks which may clarify your questions. What are we doing? Now we have this point, this position. We want to take that position vector r and resolve it in x, y, and yeah. What are we really doing? At that point P, we have an x hat and y hat. Okay, we are regarding those as our basis vectors. Next step, what do? We take this vector and parallel translate it to that point. Okay, this is all some mumbo jumbo which I didn't mention, but let me mention for your benefit now. Now you resolve this vector r with respect to these 2 basis vectors. Are you okay with that? And I claim the answer will be 1 and 2 as the coefficients. Are you okay with that?
Yes, sir.
Okay, then we do the second stage. We want to resolve the same vector, namely the parallel translate of the position vector to the point at which the P is located. And we want to resolve this into a pair of vectors along a pair of vectors r hat and theta hat. Okay, I want to resolve this long vector along this and that. I hope you will agree with me. Well, you tell me what are the coefficients. What's the coefficient of theta hat?
Theta hat is 0.
Indeed. And what's the coefficient of r hat?
R hat is root 5, I think.
Square root of 1 squared plus 2 squared. Yeah. Okay, so square root of 5. Very good. So you have solved the problem very nicely. In other words, the position vector of this point, when regarded as emanating from that point itself, can be resolved in either of these two bases, and the bases are located at that point. Now let us do something different. We go to a different point and want to play the same game. So again, we set up a coordinate basis vectors which are different from those. These are nothing to do with those previous ones, right? Because they are located elsewhere.
So this is a different x hat and a different y hat.
Indeed, very much so.
Okay.
Very good. Good point. Yeah. And you will make the further observation that the r hat over here, well, r hat points this way, r hat points in a different direction than the r hat here, right? So not only they are located at different places, they point in different ways. Yeah, I mean, this is going towards Tripura and that is going toward Himachal Pradesh or something, at least from where I am. Yeah. So yeah, these are bases at each location.
Okay. So we are saying that when considering with respect to each point, we are considering a different plane itself.
Yeah. The tangent plane at that point. Indeed, very much so. Are you okay?
Yeah, thank you, sir. Yeah, please proceed.
All right. Okay, question from anybody else? Okay, so finally, I mean, we can invert this process. I wrote r hat in terms of x and y with coefficients. You can do the opposite and express x hat and y hat as linear combinations of r hat and theta hat. Okay, so I leave that as an exercise to you, basically inverting this expression. And now I want to make the following geometric observation that unlike x hat and y hat, see, I emphasize again, x hat and y hat are basis vectors at each point of the plane, right? At the origin, there is some x hat and y hat. At this point, there is an x hat and y hat. At this point, there is an x hat and y hat. So each point has its own basis unit vectors. Of course, you can parallel translate them along from here to there and compare them to some
Sir,
extent.
I think you said something similar last day, right? That when I asked you that how are basis vectors changing with time, you said that suppose I'm taking the tangential vector as the basis vector for every point on the trajectory, like that.
Yeah, very much related. So in fact, I'm expanding on that statement here. So please observe carefully. Unlike x hat and y hat, which point in the same direction everywhere. Okay, no matter where I am located, x always points towards the east. Yeah, and similarly, y hat always points towards the north. On the other hand, r hat and theta hat, their directions change with locations. So r hat points, as I was saying, towards Tripura here, and whereas here it points towards Himachal Pradesh. Yeah, so and same applies to theta hat also. Here theta hat pointed in this direction, here theta hat points a little bit less inclined. So theta hat here maybe was going towards Punjab, this is going towards from Rajasthan or something. Okay, so this is the crucial difference between the curvilinear coordinate system, polar coordinates, and the Cartesian variables, that the unit vectors change in direction with location. And we want to quantify this. That is the next stage, to quantify how x hat, y hat, sorry, r hat, theta hat change with location. So let us begin addressing this question. So any question before I do that? Okay, if not, I just introduce this and then in the class, the position coordinate or the position vector and the velocity vector. Yeah, I want to mention what these are. The position vector of a location with coordinates x, y can now be expressed in polar coordinates. Okay, and that's what we just did. We said that the r vector can be thought of on the one hand as x hat plus y hat, but on the other hand simply as r hat. Okay. Yeah, and that happened in a simple way. We already saw it. Now we wish to find the velocity and acceleration vectors in plane polar coordinates. So we imagine that a particle is moving on the plane, its position vector r is a function of time, then its velocity vector is some r dot, which is also a function of time. We want to express that r dot vector as a linear combination of r hat and theta hat. Okay, that is our objective. Yeah. So we, of course, we can start in Cartesian variables where v and acceleration have simple formulae, because r is simply xx hat plus yy hat. Differentiating time, you will get that v is x dot x hat plus y dot y hat. And similarly, differentiating once more, acceleration is x double dot x hat plus y double dot y hat. Okay. Next time, we will see how these formulae may be re-expressed in polar coordinates. So that is as much as we have time now for. So we will meet again on Thursday. Any questions? Your second problem set is due tomorrow evening, so please hand it in well in advance. I will see you again on Thursday. Any other questions?
Sir, in problem set 2, sir,
Yes.
the first problem, are we supposed to derive the determinant expansion, or can we use it directly?
See, if you're going to use some concept that we have not introduced, then you must show that it is relevant. Yeah, so if you want to write something as a determinant, well, you should show that that is true. I don't mean do some very gory detailed derivation, but I do want you to find out the components of a proposed vector, which may be the cross product. I want you to calculate the components using the properties of x hat, y hat, z hat, and so on. You cannot simply assume that there is some formula in terms of determinant and use it. Is that clear?
Sir, one thing which I was asking was like, I can prove the formula of determinant, but the determinant formula requires some, there's some calculations regarding the flipping of vectors, which is like what is a negative volume. I cannot explain that fully.
Yeah,
I mean,
see,
it is explainable, but it is
look,
not
see,
explainable with this. Yeah.
Look, see, the question is very simple. You're given two vectors A and B, which have some expansion in terms of x, y, and z components. And we know how to compute cross products of x hat, y hat, and z hat. Using those, you should be able to compute the components of A cross B. There is no determinant here. There is no volume here, nothing. If you wish to use such concepts, you have to introduce them appropriately.
The only problem is, sir, I'm facing, I don't know whether I can use distributivity of cross product. Can I use that?
No, distributing over addition, you are welcome to use. That's okay.
Oh,
Yeah.
Thank you, sir.
Yeah, you can use that. No problem. Any other question?
Yes, sir. Problem number.
Sorry, one at a time. Kaustav, are you finished? Do you have anything?
Sir, I wasn't speaking.
Okay, I'm sorry. Then Ankon, you had something?
Yeah, sir. Can you show one utility of this r hat? And I mean, such an example where we cannot work without r hat and theta hat.
Sure. That's coming up. We will see examples next time. Yeah, we'll see in the particle motion example. We will see its utility. Okay. Sure. Yeah, okay. And in the coming days also. Yes.
So this is regarding problem number 3 in the assignment. Is there any reason as to why you left out the definition as to why if two of the subscripts are equal, as in epsilon 113 or epsilon 112, then the symbol will take the value 0. So do we derive that? Because
you need to derive anything that has not been mentioned. You have to derive. Yeah. So I have given a complete definition of epsilon. Anything else, any other property should be deducible from that. Otherwise, the problem itself is wrong. And I don't believe the problem is wrong. So please think again about it. You are on the right track. You need to think how you can get your deduction from the definition I have given.
Yes, thank you, sir.
Okay, great. Anything else?
Sir.
Yes.
Can we use something which we found in the previous sums and just say, I found this in sum 2, so I'm
yes, you can. Yeah, if you have found it in a previous question, either in this answer sheet or in the problem set one, you can use those properties.
Okay.
Yeah.
Okay. Thank you.
Yes. Who was speaking?
Harini.
Harini Ram.
Harini.
Okay, fine. Yeah, you can use that. But provided you actually did it. If you skip that question, I'm sorry. Okay.
So
All right.
today up till what time are you present in your office?
I am here till evening. So yeah, can come.
Okay, okay.
Yes, yes. As I said, people in Chennai, sorry, at CMI, please do come and meet me. Not as a group of 15, but one by one at random times. I just want to make your acquaintance. Okay. Thank you. So please go ahead for your other classes and have a good afternoon.
Sir, one thing,
Yes.
last thing. So how many points? What is the region of points that a single polar basis can express?
I mean, an infinite number of points. What do you mean? Every point on the plane is going to be every vector can.
For a fixed polar basis. For a fixed polar basis, one single unchanging polar basis.
Yeah, but at that point, see that polar basis is a basis at that point P, right? At that point P, there are many vectors. There are many vectors emanating from the point P. All of those vectors can be resolved in this basis. So let me draw a picture here. I have this point P. At the point P, I have predefined an r hat vector and a theta hat vector. They are properties of the point P. Do you agree with
Sir,
me?
screen changing. I don't. I cannot see this.
I'm very sorry. The screen has lost its. Yeah. So can you see here? I have a point P. I have an r hat vector and a theta hat vector. They are properties of the point P. Do you agree with me so far?
Yes, sir. Could you please describe? Show me
Now,
for an example. Describe another vector using that basis.
Yeah. So in this, at this point, there are many vectors emanating, like this vector, that vector, that vector. Yeah, there are infinitely many vectors. All of them can be resolved in this basis. They will have different components.
Okay.
So it's very useful. There are lots of vectors at that point. Yeah, they may all be the velocity vectors of a particle that is located there and moving in some direction. You want to express its velocity in this basis. So for that purpose, it's very useful. Okay. If any other questions? Okay. If not, thank you for your interest and attention, and see you on Thursday.
Thank you, sir.
Yeah, you're very welcome.